this video, we're going to introduce the strategy of implicit differentiation, which is going to allow us to take derivatives in more general situations. And then we're also going to talk about a way we use implicit differentiation to solve problems that we refer to as related rates problems. So these are going to be problems where we have an input variable, an output variable like we normally do, but each of those variables is thereby dependent upon a third variable, typically what we think of as time. So we're going to take a problem that originally had two variables. We're going to think of it in terms of three variables and how all of those variables are related to one another and how their rates of change are related to one another, aka their derivatives. So let's start with this idea of implicit differentiation. What does this mean? Well, let's think about how we've taken derivatives so far. So far we've only taken derivatives where y was isolated, it was already by itself, or potentially the equation between inputs and outputs was written in function notation. So f of x is equal to some expression involving our input variable x. So in these cases, we have what we refer to as an explicit relationship between x and y. So x is our independent variable, our input, y is our dependent variable, our output, and if we have y is equal to, well, we know exactly how our outputs are related to our inputs. There's an explicitly defined relationship between inputs and how you use those inputs to get an output. Now, in some cases, we may have an equation where y is not isolated. So we have a relationship between inputs and outputs, but it's not defined as clearly as it may be if we have something in function notation, or if we have something where it's just y is equal to something involving x. So we have an equation that involves our two variables. There is a relationship between them, but we would say that there is an implicit relationship between them. In other words, we can't say just looking at our equation, this is what y is equal to in terms of x, because they're both in the middle of the equation. So we're going to use a different differentiation strategy in order to find the derivative of y with respect to x when our variable y is not isolated. So we're going to use some of the same strategies we've used already, just in a slightly different way. So when we use this strategy of implicit differentiation, what we're doing is we're taking into account that y, even though it's not isolated, y is a function of x. In other words, y is dependent upon x. Y is its own output, its own function, and it's taking x as an input. Even though we don't explicitly know how y and x are related, we do know that y takes x as its input, and then it represents the resulting output. So we're going to use this general idea, and then we're going to apply one of our derivative rules, specifically the chain rule, where we think of y as the inner function. So in other words, if we have an expression involving y, not just y by itself, but other things are being done to y in our equation, we think of that as a function of y. Well, y is also a function of x. So we differentiate the function involving y, like we normally would, but then we have to multiply by whatever the derivative is for y with respect to x. So we think of y as the inner function for a function composition. We differentiate the function as normal, whatever that function is involving y, and then we take the derivative of y with respect to x, what we normally write as dy dx. So all of that sounds probably a little bit confusing at the moment. It's going to be more helpful to look at it in the context of an example. So I want to start with an example where we can actually differentiate both the normal way, what we're used to doing, and then also using this strategy of implicit differentiation. So one is going to look a lot faster than the other, but there will be certain situations where only one strategy is really going to be acceptable, is really going to be feasible. So for our first example, we want to consider the equation y cubed is equal to x. And the goal is to find dy dx, the derivative of y with respect to x, in two different ways. So the first thing we're going to do is take a moment to algebraically manipulate this equation to isolate our y, and then differentiate like we normally would. And then the second strategy is going to be differentiating implicitly, so introducing this new strategy, which I'm going to show you via an example. So for our first strategy, we want to isolate y, get y by itself, and then find the derivative the way we normally would. Now, why do we have to isolate y? Why does it work that way? Well, if we're differentiating with respect to x, we're thinking of x as the thing we're differentiating. So we want the expression, the whole expression involving x. Here, we have other things being done to y. The goal is to see what's the actual effect on x, since that's the variable that we're differentiating with respect to. So having y by itself is important so that we can differentiate that expression involving x. So our original equation, y cubed is equal to x, we can actually isolate y in just one step. All we have to do is take the cube root. So I'm going to take the cube root of both sides of this equation. Now you may remember when you take a square root in an equation, you have to put a plus or minus on one side. The cube root does not work that way. So when we take a square root, we put the plus or minus in order to indicate that you could square a positive number and get an output, but you could also square the same negative number and get the same output. That's not going to be an issue with a cube root. When we take the cube root of a number, there's only one value that applies. So we don't need a plus or minus in this case. Now, how does taking the cube root help us? Well, if we want to eliminate a cube, we take a cube root because those are inverse operations. And so we're left with y is equal to the cube root of x. Now, normally when we differentiate something with a radical, we like to start by putting that in exponential form. And so a third root would be the same thing as a power of 1/3. And so that's going to give us the form that we can differentiate from. So I'm taking the derivative of y with respect to x. Y is now isolated, and we know what y is equal to in terms of x. So we're differentiating this expression involving x because x is our variable of differentiation. So we can use the power rule here. So bring down the 1/3 and then decrease our exponent by 1. So 1/3 minus 1 is going to give us -2/3. And so typically we don't like to leave our answers with negative exponents, which means we're going to take this, move it to the denominator, and then make the exponent positive. So the simplified form of the derivative is going to be 1 divided by 3 times x to the 2/3. That's going to be our derivative. And notice once we got to the differentiation part, it was just like we've done before. The only thing that changed is we had to start by isolating y in order to put it into the form that we're used to differentiating. Now, there's another strategy that allows us to bypass this particular portion of the problem, having to isolate y. So in this case, isolating y was fairly straightforward. We will also have equations where isolating y is not really feasible, though. So taking a derivative implicitly, even though for now it's probably going to look a little bit more complicated, is going to save us time in the end as our equations become more complicated. So here's the idea with implicit differentiation. So I'm going to write down my equation. Now, rather than solving for y and then just immediately taking the derivative of y with respect to x, I'm going to apply the differential operator to both sides. Remember, this is kind of like the verb version of a derivative. If I see this, this is telling me to do something. It's telling me to take the derivative. Now, whatever I do to one side of an equation, I have to do to the other side of the equation. So I want to take the derivative with respect to x of each side of this equation. So I want to take the derivative with respect to x of the left-hand side of the equation, which is y cubed, And then I also want to take the derivative with respect to x of the right-hand side of the equation, which is just x. Now on the right-hand side, we differentiate like normal. It's basically the same thing as saying we have x to the 1/3 power. We have an expression involving x. We're differentiating with respect to x. And so we just take the derivative as normal because our variables match in this case. Now, that's not the same thing that's happening over here, because now we have a function involving a variable, but the variable is not the one we're differentiating with respect to. We're differentiating with respect to our input, and we know y represents our output variable. So here's how we get around that. We're going to treat y cubed as something where we would apply the chain rule. So I want you to think of y cubed kind of like this. Think of it as some function cubed, and imagine how you'd use the chain rule to differentiate something like this. So if you were going to take the derivative of something like this, well, you'd bring down your 3, and then you'd leave your inner function as is, and then it would become a square. So you differentiate the outside function, leave the inside function alone. But then we know you also have to take the derivative of the inside function. So I'm just going to write it that way. We also multiply by the derivative of the inside function, whatever that happens to be. So that's how the chain rule applies in any situation, regardless of what kind of function we're looking at. That's exactly what we're looking at here. Y is not just a variable. Y is actually a function of that variable of differentiation, x, and we have to keep that in mind. We could also think of y like this. Y is a function of x. We're differentiating with respect to x, but we have to take into account that we don't have an x apparent right here. We have y, which is a function inside of that function that cubes. So here's how the implicit differentiation is going to work. Forget for a minute that it's a y. You can essentially forget for a minute that's a y. Take the derivative like you'd normally take it. So if this were an x, we would just use the power rule like normal. So we'd bring down our 3. We would decrease the exponent by 1, so that would become y squared. Okay, but then, again, we have to take into account that y is not just a variable. Y is actually a function. And so it's a function within that power function, within that cubing function. So we take the derivative like normal, but because what's inside that cube is also its own function, we also have to take the derivative of whatever that function was and multiply by that derivative. Well, what's the derivative of y with respect to x? Well, it's just that. It's the derivative of y with respect to x, which we write as dy dx. Think of it kind of as distributing this to the y that we're thinking of as our inner function. So where we have y, we're applying this operator, we're applying this operation that says take the derivative, we're applying it specifically to that inner function of y. And so this is where our dy dx comes from. Now on the other side, because our variables match, we differentiate like normal. We're taking the derivative with respect to x of something involving x. And so here, think of it as x to the first power. Okay, so we just bring down our 1, the exponent decreases to 0, and there we go. Okay, so what do we do from there? What's going to happen from there? Well, we need to isolate dy dx. So what was the goal? The goal is to find the derivative of y with respect to x. Well, we have it, but it's in the middle of the problem. So think of it as a factor in the middle of the problem that is now being multiplied by 3y squared. So I'm going to divide both sides of the equation by 3y squared in order to isolate that dy dx. So here's my dy dx. It's isolated. The goal was to find it, to solve for it, so we've solved for it. And it is equal to 1 over 3y squared. Well, this doesn't look like the same thing as this, right? Because it's not in terms of x yet. So if we wanted to prove that these two really are the same thing, well, we can use the fact that we know that y is equal to x to the 1/3 power. If we were to substitute that into this expression, we plug in x to the 1/3 and we're squaring it. Anytime we raise a power to another power, we multiply those exponents together. So x to the 1/3 raised to the 2nd power, 1/3 times 2 is going to be 2/3. And so we end up with the same expression for the derivative. Now, ending up here, though, required us, in a sense, knowing how y would be differentiated, or how y would be solved for, rather, to begin with. So what if that wasn't possible? Because again, as I mentioned a moment ago, the idea is that we're going to use this strategy when we can't isolate y, when that's not really an option. So what we're going to find in a lot of these implicit differentiation problems is that once we get to this point, we're going to stop. We're not going to be able to actually write everything in terms of our independent variable x. We're just going to differentiate and then isolate our derivative dy dx, and then just write it as some expression that may involve x, it may involve y, it may involve both. But the goal is to use this idea that y is not just a variable, it's a function. It's a function that takes x as an input, so it's its own function within another function in this case. In this case, it was a power function, the cubic function. So we differentiate the outer function like we normally would, and then our inner function of y, we also multiply by its derivative, and the derivative of the inner function, the derivative of y with respect to x, that is ultimately what we're interested in. And then we just work around to isolate that derivative of y with respect to x. So that's the general idea. Now we're going to do a couple more examples, but I want to generalize the procedure for implicit differentiation. What do you have to do? We did all of these steps here, but what do you do for a more general situation, maybe when the equation becomes a little bit more complicated? So again, we're going to fall back on this idea that y is not just a variable. Y is a function that takes x as its input. So any expression involving y is then a function inside of a function. Anytime we have a function inside of a function, we have to use the chain rule in order to differentiate. So the first thing we want to do anytime we're going to apply implicit differentiation once we have an equation involving x and y, number one, we want to differentiate both sides of the equation with respect to our specified variable. So typically it's x, it could be t, it could honestly be any variable we want. So we're going to take the derivative with respect to whatever our variable happens to be. Think of applying that, think of it as an operation, it's telling you to do something, applying that to both sides of the equation, thereby balancing the equation. So you're going to apply the standard derivative rules. Our power rule, our product rule, our quotient rule, all of those things that we know how to use, we just have to apply them in a slightly different way. Anytime an expression involving y is differentiated, something like that y cubed we saw in that previous example, we also have to multiply by the factor dy dx in order to indicate that y is not just y is really a function of x. And so if we're applying something to y, we're applying something to a function. We then have a function inside of a function. We use the chain rule. So we have to take the derivative of y, the inner function, with respect to x, and that's just going to be a factor. All you really have to remember, though, is anytime you differentiate something involving y, make sure you multiply by dy dx in order to indicate that, again, y is not just a variable, y is a function of that input variable x. So you're going to apply your rules, differentiate term by term by term, depending on what you're looking at. The next thing you need to do, because the goal is to find dy dx or dy dt, whatever variable we're differentiating with, dy with respect to that variable. So you may have more than one term that now has this expression in it. You want to identify all the terms that are going to have that expression contained inside of them, and then you want to isolate them. So get them together on one side. Isolate all terms involving dy, dx, dy, whatever, on one side of the equation, and then everything that doesn't have this expression goes on the other side of the equation. And then if necessary, it wasn't necessary for the previous problem, but it may be necessary here. If necessary, you want to factor out dy, dx, dy, dx, and then divide by what's left over in order to solve for it. So essentially, you're going to treat it as a common factor. If every term on one side of the equation has a dy, dx, well, it's common. You can factor it out, and then you'll divide by whatever's left over after you factor it out, which then solves for your derivative. And again, as I mentioned a moment ago, you may end up with a derivative that looks like this. It may be a derivative that involves y and not just x. That's kind of the nature of implicit differentiation. If we could isolate y, then this strategy wouldn't be needed. But if we can't isolate y, then we can't do something like this and simplify everything and write it in terms of x. So typically when you differentiate implicitly, you're not going to be able to get down to just x, just the input variable. Typically it's going to be some combination of x and y. So let's try an example. So for this equation, y cubed plus x squared times y to the fifth minus x to the fourth is equal to negative 11. So we have our x, our y. We have an implicit relationship between them. Two different things. So number one, we want to find the derivative of y with respect to x using implicit differentiation. And then we want to find the slope of the tangent line to our curve at the point 2, 1. Okay. So why would we need implicit differentiation here? Well, the only way you could do this derivative, the derivative of y with respect to x, for something like this, using the normal strategy, is if you could isolate y. Well, notice we have y twice, and we don't have just a single y. We have a y cubed, we have a y to the fifth power. Needless to say, isolating y would be complicated here. And what you'll also find is that even if you can isolate y, typically isolating y is going to result in a very complicated expression for whatever is left over, something that would be very difficult to differentiate. Whereas y cubed, we can just use the power rule. Well, here we've got some exponents. We've also got a product, so we can just use a basic product rule. We can use another power rule here. Each of these individual terms is fairly straightforward to differentiate. But if we were to isolate y, we're not going to have something this simple. We're going to have something very complicated, something that would be difficult to differentiate. So implicit differentiation is our best option. Okay, so we want to find the derivative with respect to x. So we're going to apply that derivative operation to both sides of the equation. So we're applying it to the left-hand side, so y cubed plus x squared, y to the fifth, minus x to the fourth. Okay, and whatever we do to one side, we do to the other side as well. So take the derivative with respect to x, also of negative 11. Now, first off, if you look at the right-hand side, we're just taking the derivative of a constant. Notice there's no variable involved, period. The derivative of a constant is always just 0. So that means the right-hand side is just going to be 0. Now, I'm going to break the left-hand side down just a little bit more so we can go term by term by term. So remember, the sum and difference rules tell us we can differentiate one term at a time. So I can just look at the derivative of this term, just look at the derivative of this term, and just look at the derivative of this term. Another way to think of it is think of this operation as, in a sense, distributing to each of these terms. So rather than taking the derivative all at once, I want to break it up and just apply this operator to each of the individual terms and write out what that's going to look like. So I'm going to take the derivative with respect to x of the first term just by itself. Now I'm adding the next term, so that means I'm also going to add the derivative. The derivative with respect to x of the next term, so x squared y to the fifth. And then my last term is subtracted, so I would subtract its derivative, so the derivative with respect to x of the last term, x to the fourth power. And then again, as we discussed a moment ago, when you differentiate a constant, there's no variable involved, its derivative is just 0. So the benefit of splitting things up is now we can really just look at one term at a time and forget about the rest of the problem, at least for a moment. So let's start with the first term. So the derivative with respect to x of y cubed. Well, we actually just differentiated that on the past page, on the last page, last example. So remember, we're going to think of this as just a function, differentiate it using the normal rules, but then we have to remember that y is not just a variable, y is a function of x. So we also have to treat it as its own function, as the inner function for this cubing function. And so we have to multiply by the derivative of that inner function, y, which we call dy dx. So differentiate like normal, so that would be 3y squared. Y is our inner function, so we need to take its derivative as well and multiply by that derivative. Well, the derivative of y with respect to x is just the derivative of y with respect to x, dy dx. Okay, so that's that term. Now, for our second term, we need to think of x squared and y to the fifth as separate functions that are being multiplied together. So that means we need the product rule in this case. So we're going to add, and I'm just going to go ahead and open up a big set of parentheses, and everything in this set of brackets, parentheses, is going to be the derivative of this product. So we know the product rule says take the first function, multiply it by the derivative of the second function, and then add the first function's derivative multiplied by the second function as is. Okay, so our first function, our second function. So product rule, we have the first function, so x squared, times the derivative of the second function. So remember, y to the fifth, y is not our variable of differentiation, it's a function containing it. So we take the derivative of that expression like normal, so 5y to the fourth. And then we have to remember y is a function. It is a function within that exponential function. So we have to multiply by the derivative of that inner function, so dy dx. So all of this, forget about the x squared, all of this is the derivative of y to the fifth, but the power rule tells us we multiply by that first function. Now the power rule also says that we then add on the derivative of the first function. Now that's just in terms of x, the variables match, so we differentiate like normal. So that's just going to be 2x. And then we multiply by the second function as is. So multiply by y to the fifth power. So all of that is the derivative of this particular function. So just to recap, first function, derivative of the second function. Now the second function was a function of y, which is itself a function. So outer function is that fifth power. So bring down the 5, decrease the exponent, leave the inner function alone. But the inner function, again, is a function of x, so we differentiate it with respect to x. So we multiply by the derivative of y with respect to x. And then we add the derivative of the first function times the second function not differentiated. And then our last term just involves x. So we differentiate this like normal because we're differentiating with respect to the same variable. So minus 4x cubed. And then all of that is equal to 0. So let's clean all of this up just a little bit. So that's going to be 3y squared dy dx plus all of this. So I'm going to rearrange these. Typically we write our constant first, and then we write our variables in alphabetical order. So x squared, y to the fourth, dy dx plus 2 times x times y to the fifth minus 4x cubed is equal to 0. Okay, so we've taken our derivative, we applied our derivative rules, and then again, anytime an expression involved y, which we had right here and right here, we multiplied by that derivative of y with respect to x in order to indicate that y is itself a function, and so we have to take the derivative of that inner function. So the next thing we need to do is isolate all the terms that have a dy dx on one side of the equation. So notice we have 4 terms. 2 of them involve dy dx, and then 2 of them do not. So these 2 terms, we want to go ahead and move over to the other side of the equation in preparation for solving for dy dx. So our first 2 terms, we're going to leave where they are. So 3y squared dy dx plus 5x squared y to the fourth dy dx. And then I'm going to add this term and then subtract this term. So positive 4x cubed minus 2 times x times y to the fifth power. Okay, so the next thing to do, once we have all those terms on one side, everything else on the other, we're going to factor out that common dy dx on the left-hand side. So notice, it's something that these 2 terms have in common. It's not the only thing they have in common, but it is the thing we want to solve for. So all we need to worry is about factoring out is what we want to solve for, which again is that dy dx. So I'm going to factor it out from both of those terms, and then I'm going to write what I'm left with. So from the first term, we're left with 3y squared. And then from the second term, 5 times x squared times y to the fourth power. So plus 5 times x squared times y to the fourth power. And all of that is equal to 4x cubed minus 2x y to the fifth. So the thing to notice now is that we have a factor multiplied by this factor of dy dx, something multiplied by something else. Well, anytime we want to isolate one factor that's being multiplied by another factor, we just divide it out. So to isolate our dy dx, we're going to divide out everything here in brackets. So 3y squared plus 5x squared y to the fourth. Notice I'm not dividing just one term at a time. I divide the whole factor. And whatever I do on one side, I have to do on the other side. So 3y squared plus 5x squared y to the fourth. So that eliminates that factor and leaves us with our dy dx. So our derivative of y with respect to x is all of this. And notice, it is an expression that involves both x and y. We're going to have to leave it in that form. Unless we knew what y was equal to, we could substitute in that case. But here, based on the fact that we have an implicit relationship where y would not be easy to solve for, there's no way to know exactly what y is equal to. So we just leave this expression in terms of both of those variables. So 4x cubed minus 2 times x times y to the fifth power divided by 3y squared plus 5 times x squared times y to the fourth power. It's complicated. It is a complicated expression for our derivative. But notice, overall, it resulted from pretty simple derivatives. This was a pretty simple derivative, just the power rule plus that chain rule that we apply here. Here was a product rule, so a little bit more complicated, but the individual derivatives inside that weren't too bad. And this one was just a standard product rule as well, or excuse me, a power rule. So overall, the individual derivatives were not especially challenging to find, but the final expression for our derivative is fairly complicated, which is why the implicit differentiation is helpful. As complicated as this is, if we were to find a way to isolate y, we might end up finding an even more complicated version of this derivative. So this, believe it or not, is actually probably simpler than what we would get otherwise. So what were our next directions? The next thing we wanted to do after finding the derivative is to find the slope of the tangent line to the curve at the point 2, 1. Well, remember when we first talked about the derivative, it represents the slope of the tangent line to the curve of our function, to the graph, at any particular location. So in this case, this is our x, this is our y. Now what's different here is normally when we want to find the slope, we just plug in our value for x, right? So we have a derivative which involves the variable x, and typically when we take the derivative, that's going to be the only variable we see. So we sub in our value for x, and then we can find the actual slope, treating the derivative as the formula for slope. Well, here our derivative has two variables. It has both x and y. So that means when we find the slope, we're going to have to plug in both the x value and the y value for the particular point in question. So let's flip over. So we want the slope of the tangent line at this point, and I need to recopy our derivative. So we want dy dx, and I'm going to let you flip back over to just recopy it. So our numerator is 4x cubed minus 2xy to the 5th divided by 3y squared plus 5x squared y to the 4th power. Now, one of the notations we can use here when we're using the Leibniz notation for the derivative and we want to evaluate with particular values, typically what we'll do is we'll draw a vertical line beside the expression for the derivative and then write down what we're evaluating at. So that's going to be a notation we can use here. So we want to evaluate the derivative, the formula for the slope of the tangent line, given that x equals 2 and y is equal to 1. So this will be the notation to say we're going to plug in these values to this derivative. So now we just need to sub it in. So x is going to be 2, so 4 times 2 cubed minus 2 times x times y, which is 1, raised to the 5th power. And then all of that divided by 3 times y squared plus 5 times x squared times y to the 4th power. So there's a lot going on here. So my recommendation is just simplify the numerator and then just simplify the denominator and then go from there. Don't try to type too many things at one time, because if you don't use your parentheses correctly, your calculator is not going to evaluate this correctly. So we have 4 times 2 raised to the 3rd power minus 2 times 2 times 1 raised to the 5th power. And that's going to represent our numerator. So that gives us a value of 28. Now what about our denominator? So we have 3 times 1 squared plus 5 times 2 squared times 1 raised to the 4th power. And that's going to give us 23. So 28 over 23 does not reduce, so that's going to be the slope of our tangent line. So if we could graph y in terms of x, if we could graph the function, locate this point 2, 1 on the graph, this would be the slope of the tangent line at that particular location. Now I want to try another example just using implicit differentiation, and then we're going to take it one step further and we're going to put this into context and talk about what we call related rate problems. So we want to differentiate the demand equation, x is equal to the square root of 200 minus p cubed implicitly to find dp dx, the derivative of p with respect to x. So although x is isolated, x we think of as our input variable and p we're thinking of as our output variable. So we want to find dp dx in this case. Okay, so we're going to take the derivative of both sides with respect to x. So the derivative with respect to x of the left-hand side, just x, and the derivative with respect to x of the right-hand side. And we do it to both sides to keep things in balance. So the square root of 200 minus p cubed. Okay, now on the left-hand side, the variable in our expression is the same as the variable that we're differentiating with respect to, so we take this derivative like normal, and that's just going to be 1. And then let me come over here to the side. Now, as soon as we see a radical, remember there's no radical rule, but we do have a rule that allows us to convert a radical to a fractional exponent, and then we can use a derivative rule in order to differentiate. So 200 minus p cubed raised to the 1/2. So this is what we're differentiating. Now, this is fairly complicated. There's quite a bit going on here, because notice just the basic differentiation is going to require the chain rule. But we also run into that issue with implicit differentiation because we also have our p, our variable that's not really a variable, inside of the function. So this is actually going to require us to use the chain rule 2 times. So chain rule inside of the chain rule, if you want to think of it that way. So just start the way you normally would though. So we have a function raised to a power. So we differentiate based on the power, leave the inner function alone. So that's where we'll start. So 1/2 times 200 minus p cubed, and then we decrease our exponent by 1, so that becomes negative 1/2. Okay, now we have to take the derivative of the inside function. So 200 differentiates to 0. We take the derivative of negative p cubed. So that's going to give us negative 3p squared. But we're not quite done, because remember, p is not a variable. Not really. It's a variable, but it's a variable representing a function. So it's a function in terms of x. So we also have to multiply this by the derivative of that inner function with respect to x. So we're also multiplying all of that by dp dx. So the good news here is we only see the dp dx the one time, but it also means that all of the rest of this stuff needs to be moved over to the other side in order to put all of this in the form that we want. So we could start by cleaning up some of this if we want. It's really optional. That might be a good idea though, just to be safe. So let's see if we can clean up everything here on the right hand side before we divide and solve for dp dx. So I'm going to leave the 1 on the left hand side alone, and I just want to clean all of this up. Now I already have a fraction, so I have a pre-existing numerator, a pre-existing denominator. So when I see that negative exponent tells me I'm going to move this expression to the denominator that I already have. And I can also go ahead and think of that 1/2 in terms of a square root. So negative says move to the bottom, 1/2 says it's really going to be a square root. Now what about the negative 3p squared? Well, if it helps, think of that being over 1. So that means the negative 3p squared stays with the numerator because the resulting 1 would be associated with the denominator. So this goes to the numerator, this goes to the denominator, and this turns into a square root. So our numerator is going to be negative 3p squared, and then our denominator is going to be 2 times the square root of 200 minus p cubed. And then all of that, don't forget, is multiplied by the quantity in question, dp dx, what we're interested in solving for. And so if I divide by all of this, then I'll isolate my derivative and I'll find dp dx, which is the goal of this problem. Now, what does that actually look like in this case? Okay, we can truly think of dividing by this fraction, but another way to think of division by a fraction is multiplication by the fraction's reciprocal. So dividing by a fraction, multiplying by its reciprocal are the same thing. If we wanted to divide by a 1/2, that's the same thing as multiplying by its reciprocal, 2/1 or 2. So same kind of thing here when we have a complicated fraction. If we want to divide this out, equivalently we could just multiply by the reciprocal of that expression. So when it moves over to the other side, we're really just multiplying by the reciprocal of that. So that's going to give us our derivative of p with respect to x as the reciprocal of this. So we're just multiplying 1 by that reciprocal. And so the 1 doesn't change anything, and we just have that reciprocal. So the numerator will become what the denominator previously was. So 2 times the square root of 200 minus p cubed divided by what was previously the numerator, negative 3p squared. So there is our derivative. Now it's interesting to note here, we don't actually see an x anywhere. Everything here is in terms of p. So in this case, kind of something special happened. We don't actually have an x, but we do have the derivative that we wanted. So now that we've done a couple of examples involving implicit differentiation, we want to take this idea of a variable not truly representing just a variable, but representing a function of another variable, and we want to apply it to what we refer to as related rates problems. So in many situations, our implicitly related variables, x and y, or whatever variables we have, but we'll think of it as x and y, are also related to a third variable, an additional variable, a third variable. And in most cases, it's usually going to be the variable t, which represents time. So in a lot of cases, we think of x and y as the variables in the problem, but x and y are also changing over time. So as time continues, x and y change at a specific rate. So not only is y dependent on x is the input, y is the output, they're both also dependent upon this third variable, time. So in these cases, y is a function of x, and x is a function of t, of time. So y would be differentiated in the following way. If we want the derivative of y with respect to that third variable t, in other words, we want to know how is y changing with respect to time? What is the rate of change of y with respect to time? Well, y originally is a function of x. So just like with the implicit differentiation problems, we have to think of it that way. It's not just a variable, it's a function of x. So we have to take the derivative of y with respect to x. But we then also have to take into account that x is not truly just a variable. X is a function of t. T is an input that affects the variable x. So we also have to think of x as being another function that you differentiate with respect to t, because t is the variable of differentiation in this case. So we also have to multiply by dx dt. So it's almost like using implicit differentiation twice. How does all of this fit together? Well, we're thinking of x as a function of the input t, which represents time, but we also know that x is the input for y, the variable y, which is really the function y, the function of x that we call y. So there's 3 variables. So we have to differentiate x with respect to t, and then we differentiate y with respect to its input x. And so anytime we want to take the whole derivative for that fully outer function, the actual output in our problem, we have to take into account that y takes x as its input, and then x takes t as its input. So we end up having to differentiate twice in order to get this one derivative. So in these cases, we would say that the rate of change, what we're interested in, the rate of change of y is related to the rate of change of x. Hence the name related rates. That's why we call these related rates problems. So if we're interested in the rate at which our output is changing, we also have to take into account that y is affected by x, but x is also affected by how time changes. So there's a layering effect among these 3 variables. So whenever there are 3 variables, number 1, you have to start by making sure that you understand how they're related to one another. What is truly the input? What is truly the output? Is there an intermediate variable that you're plugging into one function that also takes another variable as its input? Understand how these variables are layered, what's truly the input, what's truly the output, and make sure that you can express it algebraically, just like I did above. Because in order to be able to differentiate correctly, you have to understand how these variables are related. You have to understand their algebraic relationship. Once you know what that relationship is, then you can take the derivative. And these particular problems are typically put into the context of a real-world situation. We're talking about real variables that are related to one another, and then both related to time, to how time progresses, affecting both our input variable x, our output variable y, or whatever our variables happen to be. So let's try a couple of examples. I can't emphasize enough, you want to take these slowly. Make sure you truly understand the problem. What are the variables? How are they related to one another? What are we thinking of as the input? What are we thinking of as the output? Write down everything that you're told in the problem and make sure you can identify algebraically how your variables are related to one another. Okay, so here's our example. So a restaurant supplier services the restaurants in a circular area in such a way that the radius r of the area is increasing at the rate of 2 miles per year at the specific moment when it's at a 5-mile radius. So in other words, at the moment in time when we service a 5-mile radius, we're continuing to expand, but we're expanding at a rate of 2 miles per year at that specific moment in time when we're specifically in this particular range. So we want to know at that moment in time, how fast is the area increasing? So we know how the rate applies to the radius. This is how the radius is changing. We want to know how is the area changing? How is the area changing? How quickly is the area changing? So what are the variables and what do we already know? Well, we have 3 variables here. So 2 of them have been easily identified. One of them is kind of implicit here. It's not explicitly identified, but we can identify it just reading through the wording carefully. So we definitely have the variable r, the radius of this circular area, but we also have the area. So area is also a variable. It's also something that is changing. So A is a variable, A representing area. Well, area is dependent upon the radius. So we'll talk about that relationship in just a moment, but area is the output affected by an input of r, which represents the radius of that circular area. But we've also been told that the radius is changing at a rate of 2 miles per year. Per year means time. It means the radius is changing over time. So there is a third variable involved that affects the other two, and it's the variable t, which represents time. So it's going to be helpful to know what all of the units are as well. So we've been told that time is in years. So we have a rate per year, so time is going to be in years. Well, what's the radius? Well, we've been given a rate of miles per year, and we've been told that at a specific moment, the moment in question, the radius is 5 miles. So the radius is in miles. Well, if the radius is in miles, area is always square units. So if length, distance is in miles, area is going to be miles squared. So there are our variables. So t affects the radius affects the area. What do we want to know? What do we already know? What do we want to know? Well, we've been told the radius is changing at a rate of 2 miles per year. So that's distance related to time. Well, distance related to time, that's telling us how the radius is changing as time is changing. So we would call that dr, the change in the radius, dt, with respect to time. So we've been told that the change of the radius with respect to time is equal to 2. It is 2 miles per year. So distance is changing with respect to time. Okay, so notice the numerator and denominator match up in terms of the units. And this particular rate applies when the radius is specifically 5 miles. So when the radius is equal to 5 miles. So at that specific moment in time, whenever that happens to be, when the radius has a distance of 5 miles, this is how it's changing. At that moment in time, it's expanding at this particular rate. So we have a sense of the variables. We know time affects the radius. The radius is changing over time. We know area is also dependent upon the radius. So how are the variables related algebraically, though? That's what we need to know. Well, that is based on the fact that we're talking about a circle, and we know the circle's radius. So this is where you're going to have to go back into that treasure trove of algebraic knowledge. I know you have geometric knowledge, the stuff you probably haven't used in a while. It's going to come back. Gradually, it'll come back. How are all of these things related? Or more specifically, radius and area. The actual, what we're thinking of is the variables in the problem, the output and the input. How are they related? Well, the rule to take the radius of a circle and find its area, in other words, the total coverage of that circle, the relationship, the algebraic relationship, is that A is equal to pi times the radius squared. So area is equal to pi r squared. Now, notice you don't see t here because the relationship between t and these other two variables is implicit. T is affecting the radius is changing over time, and because the radius is changing over time, the area is changing over time as well. So A and R are affected by this variable t, but that variable t is not readily apparent in this problem. So if we wanted to think of sort of how t is affecting these things, we could think of r as a function of t. So over time, we have a particular value of r, and then area is a function of the radius. The radius is an input that gives us an output representing the area. But if r is a function of t, then a could also be written as a of r of t. So that is our relationship in terms of how t is related to each of these. Well, what is the question though? So we've written all of this down. We have a sense of how the two major variables are related. We know that time affects the radius affects the area, so time affects the area. We have one rate, we know how the radius is changing at this particular moment, but what's the question? What are we trying to find? Well, the question is, at that moment, in other words, under these particular conditions, how fast is the area increasing? There is the question. How fast is the area increasing? Well, as soon as I see how fast, fast speed related to time, how fast means we're looking at time, something related to time. And how fast is the area increasing means we're interested in area. So we want to know, how is the area changing as time changes? In other words, what is the rate of change of area with respect to time? Or what we normally call it, what is the derivative of area with respect to time? That is what we're looking for. How fast is the area increasing? How is the area changing? What is the derivative of area with respect to time? That is the question. Now, why do we have to use implicit differentiation? Because A is isolated, right? Well, we have to use the idea behind implicit differentiation because we're differentiating with respect to a variable that we don't see in the problem. So we have to keep in mind that T is there, we just don't see it. T affects R, and T also therefore affects area. So as we differentiate, we have to take that into account. So what's this going to look like? Well, we want to take the derivative with respect to T of both sides of this relationship. So the derivative with respect to T of A is equal to the derivative with respect to T of what area is equal to, which is pi r squared. Now what's going on the left-hand side? Well, on the left-hand side, we just have dA dt. We could plug in pi r squared, but we don't have to because it's already over here. So over on the left-hand side, we've just written an expression for the quantity in question, the derivative of area with respect to time. Now on the right-hand side, that's where we're actually going to have to differentiate. And think of T and R just like we thought of X and Y. So we have an expression involving the variable R, but R is not the variable we're differentiating with respect to. We're differentiating with respect to T. So we have to take into account that R is affected by this variable T. So we're going to think of this as the outer function, take the derivative like normal, and then think of R as a function that's dependent on T, and therefore take its derivative with respect to T. Now, what about pi? What do you do with that? Well, pi, remember that's not a variable. Pi is a number, and you also don't need to write 3.14. You have a button for pi on your calculator, so you're just going to use that. So think of this as just a pre-existing coefficient in front of r squared, which is exactly what it is. So when you take the derivative, just kind of forget about pi for the moment. You're going to bring down your 2. It's going to be multiplied by that number that's already there, that just happens to be pi, and then you just decrease your exponent by 1. So we have 2 pi times r. Now what else do we need? Remember, r is not just a variable, it's a function of the variable t that we're differentiating with respect to. So we treat r as the inner function, take its derivative with respect to t. So we're going to multiply by dr dt. And there is our derivative. Now notice we have 2 derivatives in this problem, and we have 3 variables represented. So we wanted to know what is the derivative of the area with respect to time. How is area changing over time? How quickly? What's the rate of change of area? When dr dt is 2 miles per year and the radius is specifically 5 miles. Well, here's our unknown. Here's what we want. We have 2 more variables now. 2 pi is just a number. That's a constant. R is a variable, and dr dt, That is variable at this moment as well. But those were values we were given. So we were told at the moment in question, R is going to be 5 miles. And at that moment, R is changing at a rate of 2 miles per year. So we have both of those values that we need to plug in order to find the quantity that we're looking for. So let's sub those in. So that's going to be 2 pi times R, which is 5 miles, times dr dt, which is 2 miles per year. And so now we just multiply everything together. Now there's two different ways to simplify something like this. There's the exact way to do it, and then there's the way that gives you a number that's a little bit more intuitive, a little bit more meaningful. So specifically because we have this value pi right here, pi is an irrational number, which means if you put pi in the calculator, all you're going to get out is an approximation. You're not going to get any type of exact value. So typically when we have pi, if we're looking for an exact value, we have to leave pi. We have to write things in terms of pi, which means the best thing we can do is just multiply the 2, the 5, and the 2. So 2 times 5 is 10, and then 10 times 2 is 20, and we just leave the pi. Because again, if we plug in anything with the pi, we're just approximating. Now what about the units? So we have miles, and we're multiplying by miles per year. So that's going to be miles squared per year, which makes sense because we're taking area with respect to time. Well, area is in miles squared and time is in years, so the rate we have makes sense. What does this really mean though? That's not very meaningful in terms of how are things really changing. So if we want an approximation, that's when we go and we just plug that into the calculator. So we're going to do 20 times pi. Now pi is right above your exponent button, so right under the clear button. Notice in blue we have a little pi symbol, so second, and then the exponent button is going to give us pi. So if we wanted to approximate, let's just say approximate to the nearest whole amount, that's going to be approximately 63 miles squared per year. So let's put it all together. What does this actually mean? So what we're being told is that at this particular moment, when we have a radius of 5 miles from the center, okay, because we're supplying over a circular area, at that moment in time when we supply a 5-mile radius, our radius is increasing at this particular rate, so we're adding customers, adding area, adding in radius at that particular rate, 2 miles per year. And if the radius is expanding at this rate, then the area is expanding at this rate based on how area and how the radius are related. So you'll notice there are several different layers to this kind of problem. Half the battle is just identifying your variables, identifying what you're actually told. If you're given a rate, you've been given a derivative. Otherwise, you've just been given a value for a variable. And then one of the most important things here is determining what the algebraic relationship is among the variables in question. This is what we differentiate. But notice you're not given that relationship in the problem. You have to determine what that is in order to be able to differentiate. So let's try one more example. So this would involve a geometric situation. Let's look at a situation, also business related, but a little bit more general, not necessarily related to geometry. Okay, so for a landscaping business, the total revenue and the total cost for yard maintenance of X homes are given by the following. So the revenue function is 1,000x minus x squared, and the cost function is a linear cost function, is going to be 3,000 plus 20x. So what we could say about the cost is that there's $3,000 worth of fixed cost, and for each yard we take care of, it's $20 worth of cost. So suppose the business is adding 10 homes per day at the moment when the 400th customer or home signs their service agreement. So as soon as we have 400 customers, we're changing at a rate of an addition of 10 homes per day to the clientele. So at that moment, we want to know what is the rate of change of total revenue, total cost, and total profit. In other words, when we're adding customers this way, we have 400 customers and we're adding 10 per day. Well, how is our revenue changing? How are our costs changing? And then how is that bottom line of profit changing? Well, we've referenced profit. First off, notice we don't have a profit function. So that's maybe a good place to start. So what is our profit function? Well, profit is always defined as revenue minus cost, so the money we make minus the money we have to pay for our bills. So that's going to be 1000x minus x squared minus the cost, which is 3000 plus 20x. Okay, so combine your like terms. The only like terms we have here are the 1000x and the 20x. Notice the 20x is going to be negative. So we have negative x squared. 1000x minus 20x is going to be 980x minus 3000. So that's going to be our profit function. So what else do we know? What have we been told? Well, we've been told that we have a rate of change, how the number of clients is changing based on increase per day, so change per day. So we have 400 customers right now. X is the number of homes, aka the number of customers, and at this moment in question, the moment that we're talking about, we have 400 customers. So X is equal to 400. And then we've also been told that we're adding 10 customers per day. Per day, as soon as you see that word per, we're talking about a rate. So 10 customers, that's X, per day, that's time. So the change in X with respect to time is going to be 10. Well, 10 what? It's a good idea to be able to write the units. So 10 homes or customers per day. And then X would be 400 homes. So we're looking at that particular moment where we have 400 customers and we're adding roughly 10 customers per day. That's what we're averaging. So the question is, if this is the scenario, if this is what's happening at this particular moment, how does that affect our revenue, our cost, and then our profit? Well, we have our functions now, so we already know what we need to differentiate. How are we going to differentiate though? Well, we have to keep in mind the relationship among the variables. So what about revenue? Let's just focus on the relationship between revenue and then X and then T. Well, X is dependent on T, so the number of homes we have is changing over time. It's a function of time. And revenue is dependent on X. So revenue is a function of X, which means it's also a function of T implicitly. So time affects X, X affects R, therefore time affects R. So we want to take the derivative with respect to time of our revenue function. And I'm just going to call it R. We want to know how is total revenue changing? What's the change in revenue with respect to time under these conditions? So if I differentiate R, I'm also going to differentiate what it's equal to with respect to that same variable, time. So I'm differentiating 1000x minus x squared. Okay, so left-hand side, dr dt, that's just dr dt, and that's what we're looking for. We're looking for the change in revenue with respect to time. And then on the other side, we're also differentiating with respect to t, but we're looking at our variable x. So here's where the chain rule comes in. Remember, x is a variable. It's the input for revenue, but x is also related to time. So we differentiate each of these as its own function, but then we have to take into account that x is dependent on t. It's a function of t, so we multiply by the derivative with respect to t. So for the first term, take its derivative like normal, so that's just going to be 1,000. But x is a function of t. X is the inner function, if you want to call it that. So we have to multiply by the derivative of x with respect to our variable in question, t. Now same thing here, take the derivative like normal, so minus 2x. X is the inner function, it's a function of t, so multiply by dx dt. And now, just like with the last example, we need to make sure we have all the values we need. dr dt is the unknown, it's what we're looking for. We want to know what is the rate of change of total revenue under these conditions. Well, we need x, and we also need to know dx dt, in other words, how x is changing with respect to time. So we have x, and we have dx dt. So we can sub in those values. So that's going to be 1,000 times dx dt. And I'm just going to put the numbers right now. We'll worry about the units in just a moment. So minus 2 times x, which is 400, times, again, dx dt, which is 10. So let's simplify all of that down, and then we'll look at the unit. So 1,000 times 10 minus 2 times 400, also times 10. And that's going to give us 2,000. 2,000 what, though? Well, it comes down to the ratio we're looking at. So we're looking at how revenue is changing with respect to time. So revenue is going to be in dollars, and then time in this case is in days. So that is going to be $2,000 per day. So if we currently have 400 customers and we're adding 10 customers a day, the resulting change in revenue is an increase of $2,000 per day. Now, once we've done that, think of that as the model for the other two ones we want to do. It's essentially the same from a structural standpoint. We're just looking at a slightly different function. So as we add customers, not only do we make more money, but we also incur additional costs that we didn't have before. Now, the fixed costs don't change, hence the term fixed, but we add on variable cost for each of the additional 10 customers that we add on. Now, how are cost and then x and then t related? They're related in the same way as revenue and x and t. So x, the number of customers we have, is dependent on time. It changes over time. And then revenue is dependent upon the number of customers we have, so it's also affected by time. So in finding the change in cost, we're going to take the derivative with respect to time of cost. And so that means we're going to differentiate the expression for our cost function. So that's going to be 3,000 plus 20x. Okay, so our left-hand side, the derivative with respect to t of cost, well, that's just dc dt, the unknown we want, the change in cost with respect to time. Now we apply our derivative rules over here. Now notice this one's a constant. It goes to 0, which means you don't have to worry about multiplying by any type of derivative. 0 is just 0. Now here, 20 times x, take its derivative, so that's just going to be 20. But x is a function that involves the input t, so take the derivative of x with respect to t, the derivative of the inner function, x, and so that's going to be dx dt. So notice here we don't actually have to sub in a value for x. We're just going to sub in dx dt. So that's going to be 20 times 10. And you probably don't need a calculator for that. That's going to be 200. 200 what? Well, we're talking about how our cost is changing over time. So that's going to be $200 per day. So our revenue is increasing at a rate of $2,000 per day, but our costs are also increasing. If we add on more clients, we incur additional costs, and so we're adding on an additional $200 per day. But notice the increase in revenue outweighs the increase in costs, so we're continuing to make more money overall. So you can probably guess, just based on how these two compare, what we expect with profit. But let's verify using the derivative how profit is changing as well. So we also want to know what's the rate of change of our total profit under these conditions when we have 400 customers and we're adding 10 customers per day. So we're going to take the derivative with respect to time of our profit function, which means we're taking the derivative with respect to time of all of this representing our profit function. So negative x squared plus 980x minus 3,000. Negative x squared plus 980x minus 3,000. Okay, so left-hand side, the derivative of profit with respect to t, which is our unknown, the rate of change of profit over time. And then we differentiate over here. Again, keep in mind, x is not the variable of differentiation. X is dependent upon the variable t. So differentiate each of these as normal and then multiply by the derivative of that inner function x. So derivative here is going to be negative 2x. X is a function of t, so times dx dt. Derivative here is going to be 980. Again, x is a function of t, so times dx dt. And then the derivative of 3,000, the derivative of any constant, is just 0. So that is going to be the expression for our derivative. Now we know x is currently 400 homes, and then we're changing at a rate of 10 homes per day. So we can sub in those values. So negative 2 times 400 times dx dt, which is 10, plus 980 times dx dt, again, that's 10. And so if we plug this one into the calculator, negative 2 times 400 times 10 plus 980 times 10. And we get 1,800. 1,800 what? Profit with respect to time. So dollars per day. And that shouldn't be surprising, because if we're adding $2,000 worth of revenue per day, but we're also adding $200 worth of cost per day, then the overall profit is going to be the difference of those two, which is going to be an additional $1,800 per day. So related rates problems are very versatile. They're actually very important to be able to solve. This is the real kind of math that a business actually is interested in. We want to know how things are changing over time. Things are not static. Things change. Prices change. The market changes. Ideally, you want to improve the profitability of a business. So analyzing how these changes take place is important. You'll find with related rates problems, you end up with a really, really wide variety of different situations where they apply. So for this particular example, notice we were given the functions to start with, whereas with the previous example we did, we had to take the variables and we had to establish the relationship among them ourselves. So it kind of depends on the situation, what approach you take, but ultimately the biggest thing to remember is we're talking about how our two key variables are additionally related to a third variable, typically representing time. So whenever we differentiate with respect to time, we have to take into account that our variables are not just variables, they're functions of time, and so we multiply by that derivative with respect to time.